Alrighty, so it's time that we introduce the fundamental theorem of calculus. Okay, and before we state what the fundamental theorem says, let me just remind you of the two pieces of the puzzle we've been talking about. So first of all, we're going to be considering a function that is continuous on a closed interval, say a to b. Now we have two notions that we've talked about recently. So the first notion is the idea of the indefinite integral. So what is the indefinite integral of f on AB? Well, it's the most general form of an antiderivative. And then here, this capital F is an antiderivative of f. Okay, so that's the notion of an indefinite integral. Okay, find an antiderivative plus c. It really has to do with derivatives. Then we have the notion of a definite integral. And the notation is very similar, but now we actually put the a and the b as the limits of integration. And what is this? Well, recall it is the signed area bounded by the graph of f of x the x-axis, x equals a, and x equals b. And recall that what we mean by signed area is that area bounded above the x-axis is positive, and area bounded below the x-axis is negative. So that's what a definite integral is. But isn't it strange how close the notation is? In fact, the only difference is that in the definite integral, I'm specifying the limits of integration. So here is the million-dollar question. What is the connection? And the connection is given by the fundamental theorem of calculus. Okay, and so we're ready to state what this says. Now I'll just say first that the fundamental theorem of calculus comes in two parts. And when you think about what the fundamental theorem of calculus is about, it's about relating indefinite integrals, or in other words, the idea of antiderivatives, to definite integrals, finding areas underneath the graph of functions. So let's see what it says. Okay, I feel like we should have a drum roll. Here it is, the fundamental theorem of calculus. Well, at least part one. Okay. So fundamental theorem of calculus. And I'll abbreviate this FTC, just in the future, FTC. And as I said, this is part one. So just like, all of your favorite movies have part 1 and 2, This is just going to be part 1 of the fundamental theorem of calculus. Okay, so the setup is exactly the same. If f of x is a continuous function, on a closed interval, say a to b. Okay, then what? What can we say? Then the function defined as follows: f of x, capital F of x, is equal to the definite integral from a to x, okay, of f of t dt is what? Well, it's continuous on this closed interval, and differentiable on what? The open interval from a to b. And then probably the most important part of part 1 of the fundamental theorem of calculus is what the derivative of this capital F of x is. And sort of suggested by the notation, it's going to be a little f. Okay, so take a minute to soak this in. Now, probably the strangest part right off the bat is this function. And I really think that we should probably say a little bit about what this means. Okay, so I'm defining a function to be what? Well, I'm fixing the lower limit of integration. That's just going to be a, the left endpoint. And then I'm just picking some x value, okay, between a and b. So notice that this function is defined for every x between a and b. Notice that what is f of a? So if I plug in a for x, well, I'm just looking at the definite integral from a to a. That's just going to be 0. Okay, so it has this kind of interesting property that f of a is 0. And then f of b is actually just the definite integral of f over this interval. But now what if x is strictly between a and b? Well, then it's just giving me a piece of the area. Okay, so let me show you a picture. Okay, so we want to look at this function in more detail, given in the fundamental theorem of calculus, part 1. Okay, so this function actually is itself, for each x, a definite integral. So here's f of x, something like that. Here's x equals a. Here's x equals b. Okay, and all I'm saying is my outputs of my function, I'm just going to fix an x. And then my output is the area bounded between a and x. So as x goes to a, this area is shrinking, and then of course as x goes to b, I'm getting more and more area, at least more and more signed area. And so I can think about how this function is changing, and the fascinating thing about the fundamental theorem of calculus is that the instantaneous rate of change of this function that's basically just giving me all of these different areas, so how the amount of area I have changes at any given second, is just given by the function. This is extremely fascinating, and it's giving a very unexpected relationship between finding areas over different intervals and actually function values. So very, very fascinating. And so we're not going to prove the fundamental theorem of calculus in its full generality, but what I would like to do is to illustrate, at least in a very special example, that it does in fact give you this function an antiderivative of a given function. So let's take a look at how that'll go. Okay, so let's look at the function x squared. This function is easy enough to digest. And what I want to do is think about this function on the interval from 0 to 1. And I want to show that this crazy function defined as a definite integral, where the upper limit of integration is actually the variable, is an antiderivative. Okay, so what are we going to do? Well, this function should be defined for any x in the interval 0 to 1. So let's just fix an x somewhere in here and actually just compute the definite integral as a function of this x that we fixed. So f of x is just a to x of x squared, or I guess t squared. And so this, you may be asking, well, why are we putting a t in here? Well, remember that the variable of integration doesn't have any real significance, okay? As long as you are consistent between the variable of integration and the independent variable in the integrand. And since we're using x actually for the upper limit, I'm just using t. So there's no confusion about what's the variable of integration and what's my upper limit of integration. Okay, so we're going to compute this definite integral by taking the limit of a Riemann sum. So the limit is n goes to infinity. Now I'm going to partition the interval from a to x into n pieces. So that's just going to be pieces of width x minus a over n. And then times, well, I'm adding up all of the heights. So this should be well, one thing that I've done that's probably very confusing is actually a here is equal to 0. So really a is just going to be 0. So I just, of course, in general it's from a to b, but I'm saying in this special case, a is actually equal to 0. So what that means is that my heights are just really x over n squared. And my base is really just x over n, because it's x minus a over n, but remember that a is 0, so it's just x minus 0 over n, or x over n. Okay, hopefully that wasn't too confusing. I'm just setting a to be 0. It really wouldn't matter. I would just kind of affect which antiderivative I'm doing, whatever my left endpoint is. So we can add up these numbers. So we can factor out, say, a 1 over all right, so let's look at the function x squared. So f of x is x squared. And let's say that we're looking at x squared on the interval 0 to 1. And my goal is simple. I said I wasn't going to prove the fundamental theorem of calculus in generality. That's really something reserved for a course in analysis. But what we are going to do is verify that it is true in a special example. And here's our example. So what I want to do is show that the function capital F of x is the integral from 0 to x of t squared dt is an antiderivative of f of x. Okay, so notice here that I'm actually using t inside the integrand, and for the variable of integration, that's just to avoid confusion because I'm saying that x is actually the variable representing the upper limit of integration. So there's really two variables happening here. There's my fixed x value between 0 and 1 that I'm looking at the area bounded below the graph of, well, x squared. And then there's actually the variable of integration that I need to give another name, so I'm just calling it t. So what's my goal? I'm going to fix an x value between 0 and 1. And then what I'm going to do is actually compute this definite integral for a fixed x. And that will give me that capital F of x as a function of x. And then I hope to show it's an antiderivative of x squared. So what is capital F of x for this x in this interval? Well, it's just this. That's nothing new. But now what I want to do is take the limit of a Riemann sum. So I'm going to use equally spaced subintervals, or rectangles with equal sized bases. And now, what is the width of each one of those bases? Well, I'm just going to take the length of my interval. I'm finding the area over 0 to x, so that's just length x, and I'm going to partition it into n equal parts. So each rectangle has base x over n, and then the ith rectangle has height I over n. I times x over n, there we go, squared. Okay, so the ith rectangle, the right endpoint, I just need to count over I factors of x over n. Okay, so I can factor out an x squared over n squared, and I have the limit is n goes to infinity of x cubed over n cubed. And then what am I summing? I'm just summing I equals 1 to n, I squared. But I know what that is. The sum from 1 to n of I squared, I have a formula for that. So this is really just the limit as n goes to infinity of x cubed over n cubed times n times 2n plus 1 times n plus 1 all over 6. And I can actually just take the limit here. Now notice again that x is a fixed number, so I can just treat that like a constant. And then the rest of this is a rational function in n. So the numerator, the leading term, is 2n cubed, if I multiply that out. And the denominator has a leading term of 6n cubed. So the limit is approaching x cubed, and then times 2 over 6, or in other words, x cubed over 3. But this is an antiderivative of f of x. It is true that f prime of x equals f of x. And this is pretty cool. And even though we haven't proven in full generality the fundamental theorem of calculus, the first part, this at least gives you significant evidence and sort of a snapshot into the inner workings of why this definite integral function, defined this way, really is an antiderivative of the original continuous function. All right, so now that we've seen the fundamental theorem of calculus, part 1, let's look at the second part. Okay, so recall that the fundamental theorem of calculus part 1 basically told us how to find an antiderivative of a continuous function. Okay, you just look at the indefinite integral from a up to some point x. And now it is in fact true that the fundamental theorem of calculus part 1 is more difficult to prove. Okay, so we really skipped the proof of the fundamental theorem of calculus part 1. We verified it for a special case. But part 2 is actually going to follow from part 1. It's really just a corollary, more or less. And actually part 2 is probably the more useful part. It's the part that's used more in applications, and it's actually used to evaluate definite integrals. Okay, so let's see what it says. Again, same setup. If f of x is a continuous function on a closed interval, say a to b, and f of x, capital F of x, is any antiderivative of f of x, little f of x, then if we want to compute the definite integral of f of x from a to b, then all we do is evaluate the antiderivative at the upper limit of integration, and then subtract that same antiderivative evaluated at the lower limit of integration. And that's it. So notice what this is saying. It's saying that we want to find the area bounded beneath the graph of f of x over an interval. All we have to do that, we don't have to take a Riemann sum and take the limit. We don't have to do that. All we have to do is find any antiderivative of f. It doesn't matter. Just find a function whose derivative is little f of x. Then all you have to do is evaluate that function at the upper limit of integration and the lower limit of integration and take the difference. It is truly remarkable and very unexpected. So before we look at some examples and maybe a couple applications, let's actually see why the fundamental theorem of calculus part 2 follows from the first fundamental theorem of calculus. Alrighty, so we need to start with any antiderivative of f. So let's say capital F of x is an antiderivative of f of x. Of course, I'm assuming we're working on this closed interval from a to b. So what can I do? Well, recall that because capital F is an antiderivative, and all antiderivatives of f, little f, differ by a constant, I can actually say that this antiderivative, whichever one it is equal to this antiderivative plus some constant that I really don't know what it is. I really don't care what it is. All I know is this was any antiderivative. So here, this is an antiderivative by the fundamental theorem of calculus part 1. So because this is any antiderivative, this is a specific antiderivative, they have to differ by a constant. Okay? That's also an application of just the mean value theorem. Alrighty, so there's where we use the fundamental theorem of calculus part 1. Okay, so then let's actually just look at what is f of b minus f of a. I mean, this is where this proof is extremely transparent, because look at what happens. This is going to be, okay, f of b, so I'm just going to plug in b, f of t dt plus c. So this is just f of b, and then f of a is the integral from a to a of f of t dt plus c. Okay, but look at what happens. So, I mean, it's kind of silly. So the first term is, well, what I'm trying to show that f of b minus f of a is equal to. But what happens to everything else? Well, I have plus c, and then I'm subtracting c. So those cancel. And then what about this other integral? Well, what is the integral from a to a of a continuous function? It's just 0, right? This is the zero width property. So I really am done. If I find an antiderivative, then to find actually the definite integral from a to b, all I need to do is evaluate that antiderivative that I found at b and at a and take the difference. And I'm done. So that's it. Pretty straightforward. That's how you prove the fundamental theorem of calculus part 2 from the first part. And like I said, really the meat of the proof is in proving that that definite integral defined function is continuous and differentiable, as we said it is, and that its derivative is in fact f of x. That really takes some analysis. That's outside the scope of our class. But at least now we have proven this second part, sometimes called the evaluation part of the fundamental theorem of calculus. And it's going to be used, as I said before, to compute definite integrals very quickly, very efficiently. You don't have to do a limit of a Riemann sum. Alrighty, so before we do some examples, I want to talk about one of the most important applications of the fundamental theorem of calculus, and that's called the net change theorem. So what does the net change theorem say? Well, first of all, I should tell you what I mean by net change. So suppose I have a function f of x. What is the net change of f of x over some interval from a to b? Well, it's just f of b minus f of a. Okay, so all I mean by net change is basically how far I am from where I started. Okay, so if f of x is the position of a particle, and I think about x as being, like the time. So I start at a point, and then as time goes on, my function changes, and then at any given time later, I can ask the question, how far away am I from where I started? That's the net change of a function over some interval. It's just the difference in where I ended from where I started. Okay, but this is really straightforward if the function is differentiable. So if f of x is differentiable, on, say, we'll just say on this closed interval from a to b, then the net change is given by the integral, definite integral, of the derivative. And now this seems really silly to say because, well, aren't I kind of doing more work if I have a function and I want to know f of b minus f of a? And so, okay, then I take the derivative and then do a definite integral. Why don't I just take the difference? Well, the applications of the net change theorem typically involve only knowing the derivative. So I know the derivative of a function, and I want to know the net change. Okay, so then it's pretty straightforward. All this is saying is that to find the net change, knowing a rate of change, knowing a derivative, I just integrate over the interval I want the net change on. So like I said, this has a lot of cool applications in physics and other areas as well. So we'll look at some examples. But before we do that, I also want to define something else as well, called the total change. Okay, so we know that the net change of a function is found just by integrating the rate of change, or the derivative, over the integral that we're interested in. Okay, and so physically we can think about this as displacement. And by displacement, I just mean how far away I am from where I started. But we also have another notion, and that's the notion of total change. And now the total change is actually how far my function travels, the distance, okay? And we get that by integrating not the derivative, but the absolute value of the derivative. And again, you should think about this as the distance traveled by the particle, if f of x is the position of a particle. Okay, so think about displacement versus distance, net change versus total change. And so notice that if my derivative is always positive, these things will be the same. But what I need to consider is the following. Let's say I start at my house and I go to work and then I come back. So I travel a path like this. Okay, so I start here, I go to work, and then I come back to my house. Now my displacement is 0, right? Because I started and ended at the same point. But the distance that I traveled is not 0. It's greater than 0. Right? It's actually twice the distance from my house to work, because I had to go from my house to work and then from my work to my house. That's the distance I actually traveled, even though my displacement is 0. So in different applications, I may want to just know the net change, how far am I from where I started, or I may want to know the total change, how far I've actually traveled. Okay, so certainly when you think about things like gas consumption, how much gas you've used or how much fuel you've used, total change is much more important, right? But if I just want to know how far I am from where I started, then I want to consider displacement or net change. All right, so here we have some functions. Notice that these functions are defined in the way consistent with what we talked about with the fundamental theorem of calculus, part 1. And so in other words, they're defined to be, well, at least to look like antiderivatives of the integrand functions. So this first function, g of x, notice that by the fundamental theorem of calculus, part 1, g of x is really defined to be an antiderivative of square root of 1 plus 2x. So what that means is that g prime of x, because this is an antiderivative of square root of 1 plus 2x, well then g prime of x is just square root 1 plus 2x. So notice how easy it is to take the derivative of a function defined by an integral. And this is really showing that the operations of integration and derivatives are somehow inverses of each other. Now, they're not precisely inverses of each other, but they satisfy an inverse-like relationship. Okay? So derivative kind of cancels out the integral sign in this case. Now for 2, it's still pretty easy, but we do need to be a little bit careful because you see that the variable of integration is t, and then the lower limit of integration is actually the variable for this function, capital F of x. So it's not exactly in the form of an antiderivative of the integrand. But what we can do is apply our properties of integrals. So we can actually switch the lower and upper limits of integration. So that'll make this 2 to x. And the price we pay is we just pick up a negative sign. And now this is an antiderivative of cosine x squared. So then f prime of x is just negative cosine x squared. But notice that it's important to get this variable into the upper limit of integration, because then it fits in with what we know is an antiderivative of this function. Okay, so for the last one, it's a little bit tricky. Okay, so what I'm going to do is I'm actually going to define what I'll call capital H of x. And capital H of x, I'm going to say is just 2 to x, the definite integral, sine to the fourth t dt. And notice that this function is an antiderivative of sine to the fourth x. Alrighty. But then what is h of x? Well, h of x is a capital H of 1 over x. Okay? So now we can just apply the chain rule. So what do I mean by that? Well, h prime of x is just going to be capital H prime of 1 over x times the derivative of 1 over x. But all of this is pretty easy to see. I'm just going to get negative, okay, so the derivative of big H is just sine to the fourth x, but I want to evaluate that at 1 over x. And now the negative is coming from the derivative of 1 over x. It's negative 1 over x squared. Okay, so there it is. That's the derivative of this function here. Alrighty, so we want to evaluate the following definite integrals. And here is where we want to use the fundamental theorem of calculus. We don't want to set up a Riemann sum and take the limit. Now, it's possible in some of these cases, but not recommended. And so this is how it goes, typically when you want to evaluate a definite integral of a function. The first step, so for this first definite integral, negative 1 to 3, the integrand is x to the fifth. That's the function that we want the area bounded between that function and the x-axis. So our goal is just to find any antiderivative of x to the fifth. Well, that's easy, right? Because an antiderivative is just x to the 6 over 6. But then what do? Remember that we have to evaluate the antiderivative that we find at the lower and upper limits of integration and take the difference. So notationally, a lot of times what you write is you write the antiderivative and then you draw this evaluation bar. You put the lower limit and the upper limit. And all that means is I'm going to take this function evaluated at the upper limit and then subtract the function evaluated at the lower limit. Okay, so what do we get? Well, we have 3 to the 6th over 6, so that's 7 29 over 6. And then minus, if we plug in -1, we get -1 to the 6th, which is 1 over 6, or 1 over 6. And this simplifies down to 364 over 3. And remember that this number is actually the area bounded between the graph of this function and the x-axis over that interval from -1 to 3. Okay, easy enough. So the trick is find an antiderivative and then just evaluate the antiderivative at the upper limit of integration and the lower limit of integration. So what's an antiderivative of x to the 3/7? Well, remember that we just add 1 to the power, so that gives us 10/7, and then divide by the new power. So that should be 7 over 10 x to the 10 over 7, that's the antiderivative, and then evaluated from 0 to 1. But that's pretty easy. We evaluate at 1, we just get 7 over 10. If we evaluate at 0, we get 0. So the definite integral is equal to 7 over 10. Look how easy that is. The power of the fundamental theorem of calculus is great. And now we can also do functions that aren't just power functions. We can also really look at any function that we know antiderivatives of, such as sine x. So what's an antiderivative of sine x? Well, negative cosine x, right? Because the derivative of negative cosine x is sine x. We want to evaluate from pi over 4 to pi over 3. Now we just need to know a little bit of trigonometry. Well, because of the negative sign, I'm going to evaluate at the lower limit first. So it's negative cosine x. Let me just write this down. So this should be negative cosine pi over 3. And then minus cosine pi over 4. But if I just move the negative in, I can just get cosine pi over 4 minus cosine pi over 3. Cosine pi over 4 is root 2 over 2, and then cosine of pi over 3 is 1/2. Okay, nothing special there. Now this last function is again a little bit tricky. So we got to think, what is an antiderivative of 1 over square root of 1 minus x squared? Well, if you think back, this looks like the derivative of an inverse trig function. And in fact, it's the derivative of inverse sine of x. Okay, and then inverse sine of 1/2. So where does sine of x equal 1/2? Well, let's think. Looks like pi over 6. Sine of pi over 6 is 1/2. And then when is sine 0? Well, that's at 0. So this is minus 0, or in other words, the definite integral is just pi over 6. Okay? So again, just appreciate how amazing it is that we can compute these areas just by knowing antiderivatives of the function we're trying to find the area underneath. Okay, so this is a great example of the difference between net change and total change. So displacement versus distance, when the function we have now is the velocity or the rate of change of the position of a particle. Okay, so recall that the displacement is just the net change. So net change, which equals, well, it's just the integral of the velocity. Okay, and we integrate the velocity. So after 4 seconds, so that's just from t equals 0 to t equals 4. So starting it at 0, going all the way to 4. And so what we really want is just the definite integral of this velocity function, t squared minus 3t, from 0 to 4. And remember that this is very easy to do, very straightforward. All we have to do is just find an antiderivative. So t cubed over 3 minus 3 halves t squared, and then evaluate from 0 to 4. And what do we get? Well, we get 64 over 3, right? We just plug in 4. Plugging in 0 will give us 0. And then minus, well, 24. So that's 16 over 2, so 8 times 3, 24, which is negative 8 over 3. So what that means, remember, this is the displacement. Now, it wouldn't really make a lot of sense if this was distance, because distance should be positive. But this displacement means that I ended up negative 8/3 steps, or whatever the units are, whether it's feet or meters, behind where I started. So I started out probably going forward, and then I ended up eventually being well behind where I started on this straight line. So in other words, if here's our number line, or our line that our particle is moving, we're going to start somewhere. And actually, interestingly enough, we don't know where we start. We don't even really care where we start. That's the cool thing about this net change. I only care about where I end up. So I go forward, and then I end up somewhere back here. Okay, so if here's the kind of x-axis, here's t equals 0, here's t equals 4. So I start out moving forward, and then I end up back here. And this negative 8/3 is this distance, the distance between where I stopped and where I started. Now the distance is going to be this whole length here. So how much I went forward plus how much I went back. And I'm going to find that by finding the total change. So that's the total change. And now to find the total change, I need to integrate the absolute value of the velocity. And to find the absolute value of the velocity, what I need to do is actually determine where the velocity is positive and where it's negative. So if I just set the velocity equal to 0, that'll tell me where it changes signs. So we have t squared minus 3t is 0, or we can factor out a t. So we see that t equals 0 and t equals 3 are points where my velocity is equal to 0. So it seems like I should be interested in this t equals 3 value. And in fact, we see, so if I just plug in 1, I see that the velocity is actually negative. And if I plug in something actually greater than 3, I see that the velocity is positive. Okay, so v of t is greater than or equal to 0 on this interval, and then v of t is less than or equal to 0 from 0 to 3. Okay, by just similar reasoning we used when we determined when a function was increasing or decreasing. When is the derivative positive or negative? Okay, and we know that's going to change signs at a critical point when the velocity is 0. Okay, so it looks like then this total change, I can just integrate minus v of t from 0 to 3 because the absolute value is going to be minus v of t because v of t is less than or equal to 0, and then plus the integral from 3 to 4 of just v of t. And now these integrals we do exactly the same way as we did before. So we're just going to plug in t squared minus 3t, except it's going to be negative, of course. Same thing here, find an antiderivative. Evaluate the antiderivative at the lower and upper limits of integration. And what we're going to get is actually 19 over 3. That's the total distance traveled. Not how far away I am from where I started, but that's actually how much I went forward plus how much I went backwards. And you'll notice that this picture is actually drawn a little bit backwards, just maybe to ease some confusion, that really what we have is that we're starting out going negative, and then at 3 seconds, we turn around right here. So this is really t equals 3, and then t equals 4, we end up right here. But that's just a small little point. But the point is that the displacement is just the integral, the net change. The distance is the total change. We just need to integrate the absolute value and actually break up where the velocity is positive and where it's negative and add up those quantities. Okay, so this is a pretty cool example, a physical example, of when integration is really helpful. And it actually illustrates maybe more of the idea behind integration, and that is that when you're integrating, you're just adding up a bunch of small pieces that are changing. Okay, so we have the linear density of a rod is given by this density function in kilograms per meter. So here's my rod. Okay, and it's 4 meters long, so here's x equals 0 meters, x equals 4 meters. And now, the mass, if I take a small little piece, okay, of the rod, well then the mass, a small little piece of the mass, is just going to be the density at that x value times the length. Okay, so it's density per unit length times the length. And here is x. Okay, so at each x value, that little piece of the mass has a little width dx, and it has some density lambda x. And then what is the mass? Well, the mass is nothing more. I just add up all of the little pieces of mass. Okay. Now I'm sort of, mathematicians are going to get upset because I'm kind of abusing notation of what a differential is, but really this dm is just a small piece of the mass. Okay. And then that small piece of the mass is just the density at each point times a small piece of the length of the rod at that point. And then I'm just adding up all of those values from x equals 0 to x equals 4, because it's a 4 meter long rod. Okay, so this is just the integral from 0 to 4 of 9 plus 2 root x. Okay, and then we just take an antiderivative, so 9x, and then plus 1 over root x. Okay, and then we need to evaluate that, of course. From what to what? Actually, I'm not correct with the antiderivative of root x. Yeah, so what's the antiderivative of square root of x? Well, square root of x is x to the 1/2, so I should add 1 to the exponent and get 3/2. So this should be 2 times, it's going to be x to the 3/2 divided by 3/2, so times 2/3. And then evaluated from 0 to 4. So this should be 36. Plugging in 0 makes everything 0. And then what is 4 to the 3/2? Well, let's take the square root first. So that's 2 cubed is 8. So 8 times 4/3 is 32/3. Plus 32/3. And now what is that? Well, 36, what is that times 3? I think that's 108/3. So 108 plus 32, that's 140/3. And then our units are kilograms, right? Because this was kilograms per meter, but then we just added up per meter over kind of a small change as x varied. Okay, so a small piece of the rod. This was kilograms per meter. This is in meters. So all in all, we get an answer in kilograms. 140/3, so a little less than 50. Okay, so a population is increasing at a certain rate. Okay, so that means that is the derivative. So if this is the population at any given time, so population at time t, which is in years, then what we're saying is that p prime of t, so the rate of change of p, so increasing at a rate of 200 plus 50t. And now we want to know by how much the animal population increases between years 4 and 10. Okay, so we want to know, in other words, the net change between t equals 4 and t equals 10. So in other words, p of 10 minus p of 4. Okay, but this is easy, right? This is just the net change theorem. So integral from 4 to 10, and then we integrate the derivative. 200 plus 50t dt. Find an antiderivative, so that's 200t plus 25t squared, evaluated from 4 to 10. Okay, so if we plug in 10, we'll get 2,000 plus 2,500. Okay, and what is that? Well, let's see. So 2,000 plus 2,500, that's plugging in 10. And then minus, well, 4 times 200, that's 800. And then let's see, so 4 squared, or 25 times 4 times 4, that's 100 times 4. So plus 400. So this looks something like 4,500 minus 1,200. So the population increases by 3,300. And of course the units are just, I don't think it actually says what the population is, but if this was a population of ducks, then this would be, the population increases by 3,300 ducks, or whatever the population is representing.